The region D above lies between two red lines and the red parabola y equals 4/25 x squared. It can be described in two ways. Number one, if we visualize the region having top and bottom boundaries, express each as a function of x and provide the interval of x values that covers the entire region. So notice how if we define this region as having a top and bottom boundary, the top boundary would be this horizontal line here, which has an equation y equals 4, and the bottom boundary would be the parabola here, which we're given has an equation y equals 4/25 x squared. So the top boundary, g sub 2 of x, is y equals 4, and because y equals g of x, g sub 2 of x is equal to 4. Again, this is our top boundary. Next, the bottom boundary, which we want to give as g sub 1 of x, would be y equals 4/25 x squared, which notice how is already given as a function of x, and therefore g sub 1 of x is equal to 4/25 x squared. So here we have 4/25 x squared. Of course, 4/25 could also be expressed as 0.16, so we could also express this as 0.16 x squared. And now we're asked to give the interval of x values that covers the region. So we've already defined the region having a top and bottom boundary. So now the x values that cover this region would be from here where x equals 0 all the way out to this point here. Notice how this point would have coordinates 1, 2, 3, 4, 5, comma, 4. Notice how the x value here is 5. So the intervals of x values that cover this region would be from x equals 0 to x equals 5. So here we have the closed interval from 0 to 5 for x. Now let's visualize the region having right and left boundaries. The right boundary would again be the parabola here, given by the equation y equals 4/25 x squared. The left boundary would be this vertical line here, which has the equation x equals 0. So for our right boundary, notice how we want to express it as a function of y. Right now we have y as a function of x. So y equals 4/25 x squared is the boundary to the right, but we need to solve this for x in order to have a function of y. So let's first multiply both sides by the reciprocal of 4/25. So we'll multiply both sides by 25/4, which would give us 25/4 y equals x squared. And now from here, to solve for x, we would take the square root of both sides of the equation. Notice when we do this, though, we'd have plus or minus the square root on the left side of the equation. So we have x equals plus or minus, well, the square root of 25 is 5, the square root of 4 is 2, so we have plus or minus 5 halves square root y. But notice how we are in the first quadrant where both x and y are positive. So for this piece of the graph, we only have to consider x equals positive 5 halves square root y, which means our function of y, f sub 2 of y, would be equal to 5 halves square root y. Remember, x is equal to f of y. So here we have 5 halves square root y. And now for the left boundary, we have x equals 0. Remember, x equals f of y, which means f sub 1 of y would be equal to 0. And then finally, we're asked to determine the interval of y values that cover the region. We'll notice how the lowest point in the region is here where y equals 0, all the way up to the highest part of the region, which is here where y equals 4. Which means the interval of y values that cover this region would be the closed interval from 0 to 4. Being able to define our boundaries in both of these methods is important when we begin to set up double integrals and determine the limits of integration. If we integrate with respect to y first and then x, we would use the method we used in number 1, If you integrate with respect to x first and then y, we would use the method we used in number 2. I hope you found this helpful.